Good morning. Today we're going to talk about corrosion. The idea is that it's an important part of material selection. If you don't know how your material is going to behave or what are the requirements for your application with respect to the environment, then you shouldn't even try to design. It's very hard to put together something that is general enough yet that you have some fundamental understanding, but that's what I tried to do. So I went through these books, my experience. I taught corrosion when I was working at SGH, the former company I worked for. And at the end of the day, it's very industry specific. So say you work for a chemical plant, you're going to think about corrosion in a different way than if you're designing a bicycle. And I would say in the plant business, they're going to talk about corrosion control because they know they'll have it. It's very common that you can't completely avoid corrosion. You can only control it to a rate that is considered acceptable to you, or you go and use a different material. There are materials for a certain environment that will last forever, but that is not generally the case when we're talking about large structures. So that's the outline. We're going to go through the different corrosion processes first, and then I'll have a specific discussion on structural steel and the finishes. This is going to help us when we talk about the other metals later. And I want to emphasize corrosion typically refers to a low temperature process. Oxidation is what happens during corrosion, but people will think of oxidation sometime as something that happens at high temperature. And some other people will be very specific. They'll say, I'm talking about high temperature oxidation. There's a difference in which one is wet, the other is just some moisture, and it's really involving typically a different kinetics when you're at very high temperature. So today I'm going to focus on the low temperature stuff. High temperature comes very important for industrial applications, but we're not going to go through the details of it. So there's a big breakdown, and I should say in the community, people think of corrosion as something very expensive for society, and same thing for wear. Here you have a breakdown essentially saying there's no single phenomena that's responsible for all our corrosion issues. In terms of failure rate, it's spread between general corrosion, stress corrosion, cracking, pitting, and then you have other processes involved that contribute to the failures that are reported. This is on the side, but you have a printout. So when we talk about uniform corrosion, it's not totally uniform, and we're going to go through that. When I was working to figure out design parameters, typically we'll take the mean value of loss in thickness, for example, and then we'll multiply it by 2, knowing that some areas will be more corroded than the average and some area would be less corroded. The galvanic corrosion is probably a term you've heard. It essentially means you have two metals in contact. Now, if these two metals are dry, you don't have to worry about it. So they need to be in contact and they need to share an electrolyte. That's a condition to have this galvanic or cell. So a battery is more or less of a galvanic cell, and it essentially accelerates the corrosion a lot. The common example is if you have a copper roof, you don't want to nail it with steel nails or screws. Because the two pieces, the two metals are in intimate contact, and when moisture comes in, you have a preferential attack on the small component, which is the nail. The opposite would not is not as big of a problem. So if you use copper nails or copper coated nails to hold steel, you will have a preferential degradation of the steel, but maybe not to the extent where it will completely fail at the connection. So it's the bottom line idea, and the common example is galvanizing. That's a situation where we actually use the difference in potential to our advantage. But I would say if you design something where you have copper, is a good example. Nickel is another one. Something that doesn't really form a passive layer, that is naturally protected from the environment under some conditions. That's where you want to worry about a galvanic effect, because that component, if I take steel against copper, the steel will remain shiny. The copper will remain shiny and be a very strong cathode, and the steel will not disappear, but it will definitely corrode preferentially in an accelerated way. Crevice corrosion is essentially an effect where you have a local environment. So when you have rivets or bolted connection, you don't have the same amount of oxygen in your joint or under a gasket than you have on the material that's next to it. And that difference in environment creates a different electrochemical force for reaction. And you can accelerate your process in such a way. And I believe I mentioned to you before that for pressure vessels, for example, they try to use welds that are of high quality, that don't have any little holes. Everything is painted that there's no access, essentially, for penetration of the liquid between the metals. Pitting is very similar. When you have pitting, it means that instead of corroding through the surface, you had a preferential attack in some areas. And what happens is, we talked about dendrites in the case of steel earlier, and it's the same process where you start digging a hole and all of a sudden your chemistry in the hole start changing. And if that is a stable condition, you're going to entertain it, and you're going to continue to localize the corrosion in that environment. So typically in pits we find high concentration of chlorides, higher than you'll find in the solution. And you also have a different pH. And those conditions are among the factors why the reaction continues, if you supply it with enough oxygen. There's always a number of conditions need to be met for the corrosion to continue. So for industrial applications, a lot of times, and I want to mention it because it's important, people will design for corrosion based on the experience of a specific material in that specific environment. So they will run inline tests where you take different alloys, you mount them into your pipe or your process, and you will compare them. And you can get rates per year, and most of the time your initial rate is different than the rate after, so depending for how long you do it, your level of confidence it's going to change. The process itself always involves an anode and a cathode. Even if I have a piece of steel that I throw in a bucket of water, it's end up being an anode and a cathode on the surface. So at any point in time, you'll have the corrosion anode and cathode at a specific location on the surface. And I had a video of that, which I don't know if we're going to have time to watch, but it's essentially, I take the piece, maybe over here, I have a cathode and anode combination at one point in time. Then I start digging through the depth here. So say I form a little hole, but not too deep, just a little bit of a reduction in thickness. Then I invert it. So this becomes a cathode, and I have the anode next to it. So they will interchange, but it will always be a combination of the two, anode and cathode. So it may help you think of it as there's only one thing going on here. It's an exchange of electrons. So that goes through the metal itself. And then you have an exchange in ions as well through the solution. It's always the case, even if you have a single piece of metal. It's the case when you have two pieces of metal that are the same in contact. That's our crevice corrosion. And it's the same when you have dissimilar metal, and that's our galvanic case.
They use to draw that electron going the other way.
Oh, yeah. Thank you. At the end, the idea is if you can break one of the two connections, one example is if you can use a rubber gasket between two parts, and you will also need non-conductive bolts or the anything in the flanges that will essentially isolate completely one component from the other. Then they can be in the same environment. But it's very difficult to achieve. They will do it sometime for underground piping that is protected with sacrificial anodes or impressed current. When it gets into the building, you have to break from that potential. But they need special washers, sleeves for insulation, and you're supposed to test that connection to make sure that you have non-continuity in your electrical current across it. I want to bring this one up. They say it's in dissolved sulfuric acid. I don't know exactly the pH where the transformation changes from one type to the other, but you have conditions, and we talked about that before, where the corrosion of steel will result in the production of hydrogen. And a lot of times it's not a problem, except if you have that steel that's high strength and that's susceptible to the hydrogen. So that's why it doesn't have anything to do with the mechanical properties. The corrosion reaction will take place on its own, but the product of it, if you produce hydrogen in a certain environment, then you're at risk for an embrittlement, a reduction on the mechanical properties. This is an example when I said, everything changes between the anodes and the cathode on the surface. It doesn't mean that you don't get roughness. So this is the surface of a steel beam at a connection. There's a welded connection here. It's the stow drive tunnel that essentially allow for the eastbound lane and the westbound lane to go on top of each other. So there's essentially traffic right above the tunnel, and they have a steel support structure to hold it. It's approximately 30, 40 years old. And it's been corroding because of the moisture. Although in some locations, you essentially have water from the expansion joint, leaking expansion joints. So depending on your condition, this one here is mostly condensation and moisture. What happened is you think of it as an homogeneous process, but again, you see the roughness. So you know that you have a variation in thickness. One thing that was surprising to me, and the reason I put this up, I knew when I went in that tunnel that the beams were only about ½ an inch thick. So when I started seeing those pieces, I started really to wonder, is that beam going to fall? The answer is no, it's not really going to fall, because the rust expands by approximately a factor of 5 from being the metal to being the corroded, the rust steel. So if we're looking at this as being something ½ an inch divided by 5, okay, well, maybe we're corroded 20 percent through the thickness or something like that. If it's only from one side, if it's from both sides, you have significant corrosion. There's no doubt about it. But at first, when I managed to take that piece off, I just had to rethink back. Okay, I'm really looking at the rust product. First of all, I'm not looking at the anything related to a metal here. It's not a metal anymore. But it was pretty stiff. I had the sample around for a while, but I don't know where it is. So in terms of steel, just to give you an idea, these are not going to be precise numbers, but I still want to have you go home with something you can use. I'm going to start with soy. A lot of time, if we don't know the soy properties, we'll assume, and it's not necessarily conservative, that it will corrode by about 2 mils per year. That's something that came out of one of the NACE corrosion class I took. It's not perfect. It may be just 0.5 mil per year. You don't know. It may be a little bit more, but 2 mils per year is a common number to start the discussion, essentially. Atmospheric is typically less than that. It will vary. And atmospheric corrosion is one situation where the chemistry can help you. At the limit, you have some steels that will form a protective layer under atmospheric condition. They used for some bridges. The problem there is with joints. So if you make a design based on having these weathering cycles, dry and wet, and all of a sudden you have pounding water in one area, well, that steel is not going to overperform regular steel in those conditions. So you have to avoid stagnant water, and you need to have the cycles of dry and wet. So that, it's from 0 to 0.5 mil per year. And there's an ISO standard that allows you to rate it based on the environment, the air quality and level of moisture and all that. For aqueous corrosion, that's the easiest, unless we're dealing with salt water and the seawater level effect. We're talking about 4 to 5 mils per year. As long as you have, it's essentially based on the supply of oxygen. So if you have a water that is deprived from oxygen, then all of a sudden your corrosion rate could pretty much go to 0. And that's what you have, for example, in a lot of closed loop heating systems. There'll be some corrosion at the beginning, and eventually it will almost stop because you exhausted the oxygen that you had available in your system. The finishes we'll talk about later. It's more of a solution. We talked about that. This is not atypical. People think of stainless steel as the solution. But the word says stain less. It's not stain free. It can have a lot of problems, and we talked about it before. We talked about those stress corrosion crack in the food processing plant. In this case here, this is just cladding for an airport terminal. It's cladding a concrete column essentially inside the terminal, and there were other columns on the outside that were actually more of the problem. So what happens a lot when people use stainless steel is they care about aesthetic. Not all the time. I mean, we have the industrial side of things, and then we have more of the practical side of things. So from a practical standpoint, say you build a bridge, you can galvanize it instead of using stainless steel. If that's okay with you, you just go with that. But when you want stainless steel for this, it was really a question of aesthetic. It's brushed stainless finish, so they wanted to have this appearance that's not too reflective, but sort of appealing. And they had some corrosion issues that were related to, yes?
Can I ask, when they just kind of want an aesthetic finish, what's the grade of stainless steel they typically use?
If it's not going to be welded, you can typically go with 304. But there are some, we'll go through the effect of that. There's some downside on how much chloride you can accept without pitting. It's approximately 4 times less chloride that you can tolerate with 304 as opposed to 316. So 316 is definitely a better performance stainless steel, but it does cost 1.5 to 2 times the price because it's got molybdenum in it. You always specify L, which stands for low carbon. And the idea of having low carbon is you don't react with the chromium at high temperature if you have to weld it. But that's only if you weld it. Now, lots of times supplier will have the L and supply it for you. It won't necessarily be 2 different products. But so this is not the most dramatic image, but there were more dramatic ones with respect to having a lot of darkening and a lot of staining. It just looked black in some areas. And what happened is not generalized corrosion. So when I went there and I saw these here, that was after cleaning, or they've already cleaned. So I don't have an image personally that shows how dark it was, but it didn't really look like stainless anymore. After I cleaned it, you see these little pits, and they're really deep. So it goes under the effect that we talked about of pitting corrosion, where you create a local environment, all of a sudden you're not passivated, and you're going to penetrate through the stainless steel very quickly. So if this was a pressure vessel, thin wall pressure vessel, we would be worried about that as well. And I've seen that vessels used for water treatment plants. They use free chloride. They have all sort of cleaning solutions that can be aggressive enough to create a problem of pitting of the stainless steel. This is after cleaning, the rust came back. And I did want to point it out because the rust came back because it restarted the same pits. They went through the whole process of cleaning the stainless steel, trying to repassivate it in the field, but they had these geometrical anomalies. They had the holes in there, and therefore it started to bleed again, to bleed rust. And that's even if the environment, essentially the chemicals they were using were gone. I tested for that. It was now rusting in a condition of relatively low salt content. And it's not something uncommon. It happened in that water treatment plant that I work for. They essentially cleaned everything the best they could, and it rusted again and under normal operating condition. Obviously, it was a pressure vessel, so it was relatively thick. So we had to go through some processes to find out how severe the pitting could really be as far as the structural integrity of the pressure vessel. But this case was a little bit more simpler. You clean it, doesn't work. And it's an aesthetic aspect of it, so ultimately they had to take those out. You can always re-clean it and now coat it. But the process of making that coating right with the right appearance that they were looking for is more trouble than just taking a piece of stainless out and putting a new one. This is a slide that speaks to what stainless steel to use. It depends which temperature you're at, and it depends on your chloride level. It also varies with the surface finish, but this data is for relatively good surface finish. So if you have a rough surface, if it's been blasted, you can think of it as having a lower resistance because you already have holes in it sometimes. The 304 is not here, so if you see the 304L, there's a crevice line, that's the dotted line, and this is for just plain surface corrosion. So it's about 1,000 ppm chlorides that you can tolerate with the 316L. And if you go to 304L, it's not on the chart, but I know that it's at 250. So that's where the factor of 4 comes from, between the two different alloys. And there are alloys that will take you an order of magnitude up here, and that you can actually start resisting in marine environment. Marine environment with stainless steel, lots of times they coat it if it's for aesthetic reasons. So coatings are available to preserve the appearance of the stainless when you are faced with essentially cycles of dryness and cold. Dry and wet, I'm sorry. All right, so we talked about structural steel roughly corroding homogeneously. You can have pitting corrosion with structural steel as well. The crevice corrosion is a common concept. Stainless steel can be corroding in a general sense. Most of what I've seen as issues is people not understanding all the pitting corrosion weaknesses of stainless steel, and that's why I emphasize that for you guys. When you put the alloys together, that's a galvanic series here. It has a lot of different alloys, but you can see some differences where the steels are relatively low resistance. So from here we go from left to right, we go from a less resistance to a more resistant alloy. And the steel is pretty much can react with a lot of other alloys. Bronze is one example, copper is very common, stainless steel, very common. The others are more specialty alloys, so we're not going to emphasize it. So there's one alloy for which steel is safe, is aluminum. If you put steel and aluminum together, you don't have to worry too much about the steel because it's more noble than aluminum. And in general, you don't have to worry too much about aluminum because it's protecting itself. The natural passivation layer on aluminum is preventing transfer of corrosion from other components. Now, if you have an environment, and we'll go to that very shortly, if you have an environment where the aluminum is going to be at low pH or high pH, then it will disappear on you very quickly. And I've seen that on roofs where, again, they use some cleaning products. They had this large size beam, and the beam pretty much disappeared because it was in a strong chemical environment for an extended period of time. Yes?
What about when you have, we know never to make, for example, bearing parts where you have an aluminum shaft inside an aluminum bearing.
Yep.
Right? And is that the same? That's a different kind of mechanism, right?
If you have two aluminum components, you're mostly looking at a wear issue, and we talked about it for stainless steel.
They just stick together.
Yeah, you can have aluminum is not too sensitive to galling, but it essentially does have accelerated wear, whether it's adhesion, whether it's fretting, essentially related to the two pieces have high friction together, and if they bound and then break between the surface oxide and the layer next to it, you get into a very accelerated mode of wear. You're talking about moving parts, and that's something that has been my experience, that even though you'd like to keep some materials away from each other, in practice a lot of times people combine them. It's not uncommon to have a bronze or a brass impeller in a pump with the main body being cast iron and some components being stainless steel. Sometimes what is implied is that this is going to be spinning and that you won't develop these galvanic corrosion currents. But having said that, some of these pumps, if they're out of service and submerged for an extended period of time, that's it. It's gone. You build up too much corrosion product. You've built up those reactions. Now, some will try to isolate them electrically, but I've seen cases where it wasn't even clear that it was isolated. So I'm not going to say use different alloys because it's good for wear, use the same alloy because it's good for corrosion. It's very specific to what you're trying to do, but there are compromises for where you prefer to have a difference in hardness between the component that's more prone to wear based on geometry. The balls have to be bigger than the housing that's around it. So it's kind of it's a big equation that is a lot of times you just go by elimination. I can't do aluminum on aluminum. I can't do stainless on stainless. So what's left? And then you just work from there. Okay. So I was saying the aluminum alloys are not going to be generally a problem. It's not uncommon to have aluminum not fasteners, but especially the siding components. You can have contacts between copper and aluminum and generally not worry about it. There will be conditions where it's a problem. So it's not the safest connection, but it's not a guaranteed failure either. And that's pretty much what I want to emphasize with aluminum, that it's not because it's the least resistant that you have to worry about it all the time. The same applies to stainless steel. So if I have a big structure of regular structural steel and I use stainless steel bolts, I would say in general that's a good approach, because I'm making sure my stainless steel is not going to receive a potential for corrosion from the main structural component. And at the same time, because it's resisting well the environment, it's not going to transfer it to the structural steel. If I try to do the same with copper, the reason why it's a problem is the copper has a current, a stronger corrosion current. So it will transfer more current to the structural steel. And it's kind of the basic difference where aluminum and stainless steel has fasteners in the system are not as problematic as copper, brass, and anything that contains copper pretty much. We talked about active and passive. So essentially, with stainless steel, it comes out of the mill with a passive layer, but when you go and have an attack, any kind of pitting attack, you lose it, and that's where you start having a very high corrosion rate. So we're looking at the corrosion rate here in the active zone that is more than 100 times, I'd say even 500 times as high as in the passive state. So by all means, you want to avoid it. With regular steel, let's do steel first. So we're going to look at the pour bed diagram, and the idea here is to look at the potential of applied to the metal as a function of pH and see which phase of the alloy wants to be favored in terms of equilibrium, in terms of thermodynamic. And what we find is at low pH and neutral voltage, you form the oxide, and that's what happens a lot with our infrastructures in general. So steel is not resistant to the environment. It will form an unstable oxide. If you reduce the potential, the electrical potential of the steel, you can fall into that lower zone here where it's stable. And that's used with sacrificial anodes and it's also used with impressed currents. It's essentially changing the potential on the metal to enough that the pH doesn't matter anymore. It's just very stable. Another way to do the same trick is to increase the pH, because by increasing the pH, you go off of that ionic zone, and the best example for you of that is putting the structural steel in concrete. Brings it to a pH above between 10 and 12, depending on the environment, and it essentially prevents the corrosion up until you have a crack. So as soon as you form a crack, the environment now is a local environment in which you can have corrosion, pH changing. So it's two crude way of controlling the corrosion of steel: changing the pH or changing the potential on it. Now, in terms of aluminum, we see here the aluminum will go into solution below a pH of about 3. And it will depend how much aluminum. The reason you have 4 lines is it depends how much aluminum you already have in solution. So say we have very little to begin with. So below a pH of 4, we have dissolution of aluminum in our solution. That tells you the lowest limit. It tells you how coke can be acidic, in a very simple way. And if you go to the other end, you also have a limit that's very dependent on composition on a high pH. So the rough number is 9. Above 9, you can have problem aluminum in concrete, for example, if it's wet enough. So the reason why you have those boundaries, and you can go through a bunch of books, they will tell you corrosion rates for different pH, different temperature, and all that. It's the stability of the face. If you are in the stable zone here, you essentially the metal will protect itself from the environment, but below a certain pH, you start becoming soluble. The soluble phase is the preferred condition. So think of aluminum as being good, not so good. It's a very steep variation when you go to a pH below 3 or 4. Below 4 and above 8 or 9 is where the problems are. So if you have to think about, is there going to be any situation where I'm going to have some citric acid, or is this going to be cast in concrete for whatever reason, or we use some ammonia solution and we're going to have some leftovers from cleaning. Those are the things that aluminum would be at risk for. In terms of what else to do with it, so we talked about steel primarily today, and I want to talk to you a little bit about galvanizing because it's used a lot. And the way I want to do it is relatively simple. A lot of steel has an electro-galvanizing, so I'm just going to call it EG, with a thickness, I would say, between 6 and 18 micrometers. It will vary, but it's not a lot. And if you hot dip galvanize, you get closer to the range of 2 to 5 mils. Some specs will require 5 mils. In that case, you get multiple dipping cycles. 2 mils is typically what you can get out of one dipping. So we're looking here at, say, up to 125, so 50 to 125 micrometers. Now, what happens with this is you make sure that you have a sacrificial material on the surface, so when you're exposed to the environment and you have holes that you drill or you have scratches on the surface, that it will use that layer of zinc on the surface as opposed to starting to corrode the steel. Now, it's not a guarantee that you won't have rust marks. If you really scratch a piece of structural steel that has a galvanized on it, it will typically turn red or brown. Now, it's not going to lose much thickness, and that's really what we're looking for. And an advantage of electro-galvanizing is cheaper, and it's done in the shop. It's now done a lot on the car body panels. So cars have this layer. It's treated to have a roughness, because one of the issues with galvanizing is how the paint is going to adhere to it. If you treat the electro-galvanizing correctly, you can have a layer with roughness and a mechanical advantage to connect with any organic coating that you want to put on. The hot dip galvanized is a little bit of the same issue. It's hard to have paint stick to it. One way I've seen done for large structures is they will grind the surface of the zinc layer mechanically to get the finish to do the coating. And under those conditions, I've seen warranty of up to 30 years for outdoor applications. And I believe the warranty was they will go and paint it again in the field if there's a problem. So it's pretty serious enterprise. But it's a lot of work as far as, if you have large beams to go into all the surfaces and smear essentially the surface. They were not removing a lot of the zinc, but they were definitely smearing it. One of the issues with the hot dip galvanizing is you can have degassing. So over time there'll be some gas trying to come out, and that can interfere with the adhesion of the coating on the long run. Organic coatings are typically at risk for any imperfections. So if you have scratches, if you have bolted connections, it's always going to be a problem if you're relying on a surface coating for corrosion control. Now, to give you an idea, if you do everything perfectly, you can get 25 years out of an organic coating. It'll have to be a hard epoxy that requires typically a blasting, sandblasting, to get some adhesion. And you essentially design the coating to make sure it will take years and years to penetrate, to have the moisture and oxygen penetrate all the way to the steel surface. Because when that happens, that's where you reach the useful life, because you start creating that reaction again. The reaction you're trying to avoid over time comes into play. So if you have paints that are not in continuous immersion, they're much less at risk of spallation over time. They will last much longer than if you really have stagnant water for 15 years. If you have stagnant water and you want to design for a very long period of time, in general, I've always been thinking of galvanizing, hot dip galvanizing as a good option. Not that you can't paint it, but just galvanizing per se with piping, you're looking at about 50 years of life. And there is an initial cost, but you're not as sensitive to scratches and installation issues. So I hope you get some idea, and you probably knew a little bit, in the soil, yeah, it can corrode, I don't know exactly how much. It will depend on soil conditions, obviously. Aqueous corrosion, we talked about, it was pretty much a fixed rate. It will be higher if you're at the shoreline, essentially, and by a factor of maybe 2 or 3, so you can get to 15 to 20 mils per year there. Industrial applications, they have it's a lot based on experience, temperature, the environment. They do testing. It's very specialized. We talked about homogeneous being not so homogeneous. that it's always flipping and that you always have an anode and a cathode. This is something that bothered me for a long time. So I want to emphasize there's only one way things corrode. So keep it in mind. Pitting corrosion, I gave you some examples with stainless steel. Yeah, it's going to happen with aluminum. It happens with copper. And we can go over some of the conditions where it happens. And we just talked about, finishing methods. Professor Eager has been here. I'm sure he's been taking notes. We have a few minutes. Do you want to address the class? No, not this morning. Okay, then we'll go through a little video just to make sure this stays with us.
Destructive alteration, or eating away of a metal at areas which are called anodes, where the electric current leaves the metal and enters the solution. We have the presence of an electrolyte as one of the first requirements of corrosion. An electrolyte is any liquid that contains ions. Ions are electrically charged atoms or groups of atoms in solution.
It's about 2 minutes. The idea is to show you the different components in terms of anode and cathode. And they made the argument, this is 50 minutes video, but the idea is you don't need the two components to have the same thing going on in terms of hydrogen, and all the reaction can happen on a single surface. It will be easier if you have a pit, because now you have a clearly identified anode and cathode.
An anode and a cathode, where current enters the metal from the electrolyte. These electrodes may consist of two different kinds of metal, or they may be different areas on the same piece of metal. In either case, there must be a potential difference between the two electrodes, or areas, so that electricity will flow between them. A wire or other metallic path is necessary to complete the circuit for the flow of electrons, which are negatively charged particles moving in the wire from the negative to the positive electrode. The popular concept of current flow is used in this discussion visualizes imaginary positive charges moving in the opposite direction. This electron path may be provided by any kind of a conductor or merely by the fact that metals are in contact with each other. Let us consider what takes place at the anode when corrosion occurs. Remember that the...
All right. That's all I had today. If you have questions, I'm around all morning.